All right, so filling in from yesterday, centripetal force is mv squared over r. You guys figured this out with your lab, and now we're just doing the AP style lab write-up. So what's the relationship? Centripetal force is applied by the hanging weight, the swing mass, the radial size of the circle, and a constant speed that you calculated using 2 pi r divided by time period. Because there were 4 variables, okay, check. We had to do 3 experiments. The way I had you guys do it was to relate everything to b squared, and then we put it all together at the end. So you have one of these write-ups. You guys got to grade yourselves out of 12 points. You were either figuring out the relationship between B and R, holding the 2 Plato canisters constant, or you were figuring out the relationship between the top mass that was swinging around in the speed, holding the bottom canister weight, and also the radial size constant. Right? Or you were changing out the bottom Plato canister, making it maybe heavier and heavier, and see how that related to the speed. But you kept the circle size constant for the entire lab, and you also kept the top plated canister mass the same. Right? So figure out which lab write-up you actually did. But does anybody have a question which one they actually did? Okay, so everybody knows you either did this one, or this one. Okay. All right, so let's see how you would score yourself. Measuring tools. This is the same for all 3 of these. Regardless of which one you did, you needed a ruler, a stopwatch, and a scale. Okay? So you needed that for all 3 versions. Okay? Give yourself a point for each one of those. Your measuring tools. Okay? Remember, AP, that's what they care about. Is like, what equipment are you using to measure the thing? Okay? Then the next section was data gathering procedure. A lot of these steps are also the same version to version. So the first point is just describing the lab setup. If you describe the lab setup, give yourself a point. Here's my example. Put a string through a plastic tube, secure a safety bucket to each end of the string, whirl 1 bucket mass swing in a horizontal circle so that the weight of the other bucket, force hang, like hang force, provides a centripetal force that holds the swinging bucket in a circle of constant radius. You might call that dynamic equilibrium. Not true static equilibrium. There's a net force, but the circle size is not changing. That's the same description, all 3, as long as you had a description of the lab setup. That's worth a point. Actually, most of these steps are the same, so I'm just going to zoom in on one of these and just read it. So all of these steps are the same. So you need to measure the swinging mass with the scale, measure the hanging weight with the scale. No, remember, one of these was grams, one of these was millinewtons. So different concepts, but use the scale for each of those. Okay. Also measure the radius of the horizontal circle with the ruler. So 1 point for saying that you use the ruler, 1 point for saying that how you use the scale, what you use it for. Okay. With a stopwatch, time 10 revolutions, and then divide that by 10 to determine the time period of 1 revolution. So 1 point for how you use the stopwatch. It's true for all 3 setups. Okay. Then how do you actually get the speed? Well, speed is distance over time, in this case circumference over time period. So that'd be 2 pi r divided by time period to go around once. So 1 point for saying how you determined speed. Now I put this in the data collection section. If you put this in the analysis section because it involves equations, then I guess you could justify that too, as long as you have it somewhere, how you determine the speed using like this. Okay. I said square the speed to obtain v squared. Everybody did do that to eventually make graphs that were involved. But I didn't assign point value to that, but that's there. Hey, repeat the previous few steps to find an average speed. 1 point for, say, multiple trials to reduce random error. Now, if you pay really close attention, you probably saw that I did not explicitly put that on that lab paper, so this may have been an easy detail to miss. But you guys know when you guys do a lab write-up for one of your FRQs in May, this is going to be worth 1 of your points, right? Saying multiple trials and take an average to reduce random error. Okay, and then repeat. Okay, now here's where things get different. Okay, so we're going to do 1 by 1. Okay. If you had the lab where you left the 2 canisters alone, but you were changing the radial size of the circle, right, then, well, that's what you would say. Repeat the previous steps for various values of R, keeping the swinging canister and the hanging weight constant. So 1 point for identifying control and independent variables. Right. Very similar idea with the other 2 setups, just juggle the variables around. So if you had the experiment where you were changing out the hanging weight, or sorry, no, the swinging mass, then you would say that. So repeat the previous steps for various values of swinging mass, keeping the radial size and the hanging weight constant. And then finally, the last option was if you were changing out the weight of the hanging canister, and you were leaving the radial size and the swinging mass the same, then you would say that. So repeat the previous steps for various values of the hanging weight, keeping the swinging mass and the radial size constant. Okay? So just so long as you identify what's the control variables and what's the independent variable. Here. Now, data analysis. Each of these are different from each other. So if you're in the left column, then you would have graphed v squared versus r, and that would have created a linear relationship. Now, if you figured this out by yourself, it probably would have taken like many days. So that's why I helped you guys by creating the axes ahead of time. I told you what to graph. If you're on middle section, you changing out the swinging mass, you graph v squared versus the reciprocal of the swinging mass, right? V squared versus 1 over mass. Okay? That would also create a linear relationship with a constant slope. And then the last one is you're changing out the hanging weight, graph v squared versus hanging weight, and that would create a direct relationship also with a constant slope. Right? So each of those graphs creates a constant slope situation. You guys remember that from your graphs. Okay. And then conclusion, answer to your question. So we're looking for what's directly proportional. So what you guys would have found is that if you were changing the radial size, that's the left one here, that the square of the speed is directly proportional to that radial size. If you were changing out the swinging mass, what you would have found is that there's something with an inverse relationship, but then there are actually a couple of manipulations. So v squared is proportional to 1 over swinging mass. Say the heavier the mass, the slower you swing it, according to this proportion. And then if you change out the hanging weight, you would have found that the square of the speed is proportional to that hanging weight, which was again providing you a centripetal force. So 1 point for having a conclusion that answers the question. You were trying to figure out what's each of those individual relationships. Now, if you take these 3 points of view and bring them together, you guys ever heard the allegory of the elephant? Like there's a bunch of blind people and they're all trying to figure out what an elephant is. Right? And some people like grab the trunk and like, oh, an elephant's like a snake. And some grab the legs and like, oh, an elephant's like a tree. And some grab the tail and it's like a rope, right? So that's like 3 different points of view. You bring it all together, you get the full picture of the elephant. And the answer is centripetal forces in v squared over r. Okay. So grade yourself out of 12.